So I've got this piece of plastic that doesn't seem very exciting. I can rotate it back and forth and, well, it doesn't seem to do much of anything. Let's add another. It doesn't seem to do anything, but then you rotate it, ooh, look at that. Wherever they overlap, no light gets through. So they allow most of the light through on their own, but then none together if they're rotated. These are called polarizing filters, and they're made of a bunch of tiny black lines that absorb the light in one direction, in between which are transparent lines that allow light through. Because light is a transverse wave, this acts kind of like a picket fence. You can shake a rope one way, but you can't shake it another. This makes polarized glasses great for getting rid of the glare off of tables or off of cars. Much like skipping a rock, light that gets reflected off of big flat surfaces tends to be polarized in the same direction as the plane it reflected off. So any light aligned with the filter is allowed through, and any light that is not is blocked. So it shouldn't be a surprise that two filters that are aligned the same way act like a single filter. While like the bars of a jail cell, two crossed filters allow nothing through. That jail bar or picket fence analogy only goes so far, however. Light is not a rope, it's a transverse wave, and amplitude is a vector, which means it can be split into x and y components. So we can do cool things like this. Pretty neat, huh? Putting transparent materials between crossed polarizers gives us a phenomenon we call birefringence. It's pretty complicated to explain what's going on here, but it definitely has something to do with stress. We can see that rainbow effect again with this clear plastic tube. We often use birefringence to examine the invisible internal properties of things like this lens, or this protractor. You can see where the injection molding process added stresses to this protractor. Pretty cool, huh? So that's polarization. See you next time.